Okay, so we're going to go ahead and start the class now. I put some documents up on Blackboard. Hopefully you got a chance to go up and download those documents. I put them up earlier today. If you didn't, just go to the website and open the documents up so you can refer to them while we are talking about it. So what I want to do today is to start a new topic. We're going to talk about AC power. And we'll spend today on it, and it'll take us into our next class. There's three separate topics we need to talk about. So what I have on the board are the three elements that we deal with in AC. We have a resistor, we have a capacitor, and we have an inductor. So the oppositions you guys are familiar with, resistance and reactance. We have capacitive reactance, and we have inductive reactance. So what we know about power, if you remember from DC circuits, power is a rate of doing work. Power is a rate of converting energy from one form to another. So when we look at the unit for power, power is a rate of doing work. So power is work per unit time, or I can write that as energy per unit time. This has a unit of joules. Work or energy is measured in joules. This has a unit of time, or seconds. So time is in seconds. So power is joules per second. And we remember we named that a watt. And so we did power calculations based on Watt's law. P equals V times I, and the other various forms of Watt's law in DC circuits. What we're going to learn in AC, power is kind of a complex animal. It's actually way more involved than it is in DC. And so depending on the element we have, power behaves a certain kind of way. Now, I'm using the term power, but remember, all power is the amount of energy you use in a certain amount of time. So when I refer to power, I'm really talking about energy in a given amount of time. So you can think energy, you can think power. So you can think of power flowing, but it's really energy flowing back and forth or in the circuit. If I have a resistive element, the energy flows into the resistor, and you know from experience that the resistor will heat up. And so I show this, that a resistor will dissipate power. That is, it'll take the electrical energy and convert it to heat. And so with a resistor in the circuit, as energy flows through the circuit, some of the energy is lost to the environment as heat. If I look on the other end where I have reactive elements, either capacitive reactance or inductive reactance, if I have ideal devices, perfect devices, that means no resistance, only reactance, then both of these components can only borrow power. They cannot dissipate power. They cannot take the energy and convert it to heat. So energy flows into the capacitor, energy flows back out of the capacitor. Or energy flows into the inductor, and flows back out of the inductor. Here, the energy is actually stored in the electric field that exists between the plates of the capacitor, and when that energy transfer is complete, then all the energy flows back out of the capacitor, back to the generator. On this end, the energy flows into the inductor, and it basically is stored in the magnetic field. As more energy flows into the inductor, the magnetic field builds up. And when the energy flow stops, the magnetic field collapses and the energy flows back out. And so I have the red arrows indicating energy flowing in and the blue arrows indicating energy coming back out of those reactive elements. And so I call that borrowed power. If I give you something, if I borrow, I'll give you some money and then I take it back, you still have nothing. And that's the way power is. The word dissipated means converted to heat. And so the idea here is that you understand, this is kind of the big picture where we're going with this, is that reactive elements cannot dissipate power. Reactive elements cannot dissipate power. So that's the first takeaway. Reactive elements cannot take away power. The other thing that's important that we'll get to later on in our conversation is resistive power is the only power that can do work. Resistive power is the only type of power that can do work. Now, what do we mean by work? Well, we also define that in circuits 1. You know, in order for work to happen, you have to have something moving. You have to have a force, and the force has to act through a distance. So the force has to cause something to move. So if I want to make something move like a motor, if I want to cause any kind of work to happen, that only happens with resistive power. And so if there's a good power and the bad power, really depends on what I'm doing. But if I want something to happen, if I want work to be done, then we will consider resistive power the good power and reactive power the bad power. Now, having said that, we have a measure of how resistive or reactive the power is in the circuit, and that's given by something called the power factor. And I kind of touched on that a couple classes ago, that looking at the power factor, you can tell if the circuit is resistive, if it's reactive, or if it's somewhere in between. And ideally, we want the circuits to be resistive, because if they're resistive, then that kind of power can do work, the work of lighting a light bulb, the work of spinning the motor, whatever it is we need done. If it's reactive, that kind of power can't do anything. So usually what we want to do, if we have some kind of circuit, we want to try to make it as resistive as possible. And sometimes you can't do that by just adding more resistance to the circuit. Sometimes what you got to do is remove some of the reactive power. Does somebody have a... Yeah, go ahead if you have a question. I can't see the screen. Just go ahead and you can unmute your mic.
No, I was just trying to see components behind you under power borrow.
Okay. So I have resistor represents heat being radiated from the resistor, those arrows. This represents energy flowing in and out of the capacitor and energy flowing in and out of the inductor. And remember, we're talking here about ideal devices. An actual or practical capacitor or inductor does in fact have resistance. Therefore, it would dissipate some power, it will borrow some power. But in this class, we're talking about ideal resistors, ideal capacitors, ideal inductors. So the ideal resistor takes the energy and converts it to heat. The ideal capacitor or inductor takes energy in, stores it for a certain amount of time, and then sends the energy back to the generator. And so we'll get into that as we go along into the lesson today and the next class. Now, I did put up some documents on Blackboard. I put them up earlier today. I'm sorry I didn't get them up sooner, but I have an issue with my scanner. I bought a brand new scanner, connected it to my computer, and I could never get it to work. The scanner worked just fine, but the printer wouldn't work. I went the whole semester last semester without a printer. And then I go up there the other day to use it. Now the scanner won't work, but the printer's working just fine. It just, I don't know what happened. So I really need the scanner so I can scan these documents up for you guys. But I ended up having to go borrow a scanner from somebody to get these documents up. So I'm hoping I got them all. So if you didn't get a chance, go to Blackboard. If you have an ability to print, go ahead and print these documents out. If you don't, just go to Blackboard, open them up, and we can talk about them. The very first one I want to talk about is a graph. So I know you probably can't see it in the camera, but if you go to Blackboard, you'll see it. There is a graph in the upper right-hand corner of the graph. It's titled AC Power, and it says Think in Pictures. AC Power, Think in Pictures. And I'd like for you to take that out. If you have it, take it out, put it in front of you. If you don't have it, go to the website, open it up, and look at it on your computer. And let's talk about the graphs there. Now, I'm going to try to reproduce the graph. I'm going to draw it the best I can on the board, because Collaborate has the ability to share files, but I tried that before, and I don't think that feature works too well, so I'm not going to chance it. Last time I did that, it caused the system to jam up. So I'm going to rely on the fact that you guys have this document in front of you. Again, it has 3 graphs on it. AC power, and it says Think in Pictures. All right, so if you look at that graph, what they have is in the upper left-hand corner, they have a circuit with a resistor in it, and they have those same little lines that represent basically energy being converted to heat. This shows energy radiating away from the resistor. And so the idea there is what I said earlier, that you realize that when power flows into a resistor, the power is converted to heat. You put your hand on the resistor, it'll heat up. So some of the energy that's flowing in as electrical energy is being converted to heat. And so resistors dissipate power in the form of heat. So if you go down and you look at the graph, now look at that graph really carefully. And I'm going to reproduce it. I'm not going to draw it exactly. I want you to see something on that graph. So on that graph, they have two curves. They have a voltage curve. They have a current curve. So I'm going to draw it. So I'm going to draw the voltage curve. And it keeps going. So I might think about the voltage here, V. So I'm showing the sine wave. So this is the instantaneous voltage. And then that voltage produces a current in the circuit. So I'm going to think about I flowing into that resistor. And again, I'm showing the lowercase because these are instantaneous values. And so I'm going to draw the current waveform produced by that voltage in this circuit. And so if I draw it, this is the way I would draw it. And the point is that both the voltage and the current, they zero at exactly the same points. And what I mean is they cross the horizontal axis at the same point. So they both cross here. They both cross here. They both cross here. And it continues on down the line. Now this horizontal axis is time. And this is some other quantity like power, voltage, or current. One of those. Could be either one. The idea, you already know this, that if you have a resistor, we've said this many times in the course, that if I have a resistor, the current through a resistor is always in phase with the voltage across the resistor. The current through a resistor is always in phase with the voltage across the resistor. And so I'm showing these zero at the same point, and you can see they're in phase with each other. Because they're in phase with each other, I can use this equation that we learned in DC for power. Power equals voltage times current. But I'm going to write it in the form that we're going to use it for this graph. It's the instantaneous power. It's the instantaneous voltage times the instantaneous current. So I would use the script letters like script P equals script V times the script I. Those are supposed to be lowercase script characters. And so instantaneous power, I would just take the instantaneous voltage times the instantaneous current. Now I want to give you a new concept here. This is new. This idea of positive power, and negative power. Positive power and negative power. So this is a new concept. Positive power is power that's dissipated. Negative power is power that's borrowed and returned to the system. So positive power is dissipated power. And negative power is what I call borrowed power. So positive power, we're going to have a heat situation. And some energy flows into the resistor and it's converted to heat. If I add up the energy put into a resistor plus energy that makes it through to the other side plus energy that's dissipated this heat, it's got to add up to the energy going in. The conservation of energy principle has to apply. So this idea of positive power and negative power. Now, why I bring that up is we can actually use this equation, Watt's law, on this graph, and we can get a curve called a power curve. A power curve. So I'm going to show you how you would do that, but again, you need to refer to that graph, so hopefully you have that out so you can look at it, because I'm not going to draw the whole thing. I just want you to think about how you would power from these values. And what I would do is multiply on the graph point by point. And so what I mean is, let's say I take a number here. I take that current and multiply by that voltage value. If I take this positive number times that positive number, I get another positive number up here. Or if I choose a point like right here, if I take this positive number for current and the one right above it, that positive number for voltage, I get a number up here. And I can do that point by point all the way over here for 1/2 cycle. And you can see that all my voltage values are positive, all my current values are positive. So a positive number times a positive number gives me a positive number. So the power I would get by using this equation on the first half cycle of these two waveforms gives me positive power. Remember what I said, I erased it, but positive power is power that's dissipated as heat. Well, look at what happens when I come beyond 180 degrees. If I come beyond 180 and I do the same kind of application of Watt's law, let's say I take this value for current and I multiply it by this value for voltage. Well, that's a negative value for current. That's a negative value for voltage. A negative times a negative is a positive. So I'll get a value up here somewhere. And no matter where from 180 over to 360, all my current values are negative and all the corresponding voltage values are negative. So in each case, between 180 and 360, I'm multiplying negative numbers by negative numbers. They're going to result in positive numbers. So all the values I get from 0 to 180 degrees will be above the horizontal axis, all positive. And all the values I get by multiplying these negative values for B and I from 180 degrees to 360, multiplying negative numbers times negative numbers, they too give me positive values. So with resistors, I only get positive power. And if you look at the graph, again, I'm holding this up. I don't expect you guys to be able to see it in the camera. So please, if you haven't, go look at the graph, and you'll see kind of what I drew here, waveforms for V and I, and you'll see where they did the product of the two. But you can also see that curve called the power curve. So look at that power curve, and you'll notice in the power curve that that's all positive power. That's all power that's dissipated. So that shows you, or it's trying to show you, the graph is trying to indicate to you that the power that flows into a resistor is dissipated as heat. Now, what if we change from a resistor to a capacitor? How does that affect our power curve? But let me go back over that power curve. Look at the power curve real close. I want to point out, I already pointed out that the power curve is above, the whole power curve is above the t-axis, so it's all positive power. But look how many sine waves of voltage and current we have. We got one sine wave, one cycle of voltage, and one cycle of current. That's easy to see because they're in phase. But if you look at the power, we actually have two cycles of power. The one cycle of voltage and current always result in two cycles of power. It's kind of hard to see because you have a half a sine wave in there at the beginning, the very beginning, and another half a sine wave at the very end. But if you put the portion of the sine wave at the very beginning and the very end, the middle part, it actually makes up another sine wave. So there's actually two sine waves of power there. And you'll always have that the frequency of the power is always twice the frequency of the voltage and the current. So there's nothing to calculate there. I'm just pointing out a fact. I'm pointing something out. That energy has a frequency, or the power has a frequency, the voltage has a frequency, and the current has a frequency. And the frequency of the power is always twice the frequency of the voltage or the current. You can just kind of see that from the picture. Now, what happens if we substitute out the resistor and put in a capacitor? Now, remember, I won't keep reminding you of this, but anytime I talk about components, I'm talking about ideal components. So an ideal resistor only resists current. It has no capacitance, no inductance. In reality, a real resistor does have capacitance and inductance. We'll talk about how later, but we can ignore it. An ideal capacitor has no resistance, no inductance, only capacitance. Ideal inductor has only inductance, has no capacitance, no resistance. So we're talking about ideal devices. So if I get rid of my resistor and put in this place a capacitor, how would that affect my power curve? So I'm going to replace that with this. Now let me say that the argument, I'm going to go through an argument here, and what I'm going to say for the capacitor is true for the inductor. There's only one small change you got to make, but so we only have to do one. I don't have to do the inductor and the capacitor. The way the capacitor is going to act, the inductor acts exactly the same way. So how does this behave? Now notice I don't have those little arrows here representing heat, because an ideal capacitor cannot dissipate power. It cannot take energy and change it to heat. All it can do is store the energy and then give the energy back to the system, give the energy back to the generator. And so I want to draw the curves for a capacitor. I know for a resistor, they're in phase like this. But how would I draw the curve for a capacitor? Well, that's when you got to go back to that. I told you, remember, that Eli the Iceman. So Eli the Iceman. This says that if I have an inductor, I'm going to see the voltage before I see the current. If I have a capacitor, I'm going to see the current before I see the voltage. So here we have a capacitor, so I expect to see the current before the voltage. So how would that look in the graph? So let me get rid of this graph and we'll make another one. All right, so up here we got V, I, or P. These are instantaneous values. So since I have a capacitor, I see the current first. What does that mean, I see the current first? Well, here the horizontal axis, the t-axis, that's time, right? What that says is that at t equals 0, I should have current peaking, and I don't even see my voltage until 90 degrees later. This leading and lagging, if you remember, is separated by 90 degrees. So that angle, and I showed you why. I showed you why earlier in the semester when we talked about AC oppositions. So if you don't remember why and you want to know why, go back and look at that video. It's recorded. It's on Blackboard, the website Blackboard, on the previously recorded video. So you don't need to know that. But if you're interested in why is it 90 degrees, we did go into the details of that when I talked about the derivative and calculus and all of that. And that was only to give you a deeper understanding of what we're talking about. Can you get through the class without understanding that stuff? By all means. Most people skip over it anyway. But I want you to know what's under the hood of the car, because I think if you understand what makes things operate, you have a better appreciation for what we're talking about. But for some reason, if your mind can't wrap around what we talked about, then don't worry about it. You don't really have to understand it to get through the course. We have a capacitor. Well, capacitor, the current is going to lead the voltage by 90 degrees. So on my graph at t equals 0, my clock hadn't even clicked yet, and my current is already at a peak. So I'm going to draw my current like this. So there's my current. Actually, I shouldn't have made it that big. That's too big. I want to make my voltage bigger than the current. But you get the idea. I'm going to make it a little bit smaller. So my current is at a peak. That's my I. My V is going to happen 90 degrees later. Now they have a better graph, so I'm just going to draw this so you can think about this. So the current is right here. To get the voltage waveform the right way, what I would have to do is I have to kind of push it over 90 degrees. So it's going to have and again, it's better to look at it on the graph, because I don't think my graph is going to be as good as there. You can see, well, I'm pointing like you can see it, but look at your graph, look down at your graph. You can see where the voltage starts out at 0 degrees and the current here is at the peak. So I'm going to attempt to draw what they have. They have the voltage. I guess I should use another color. So they have the voltage like starting here. It comes up like that. And if you look at these numbers, now you look at the graph as I talk about this. Like if I'm right here, let's say I take a value for V and I. If I take this value for voltage, that's positive. If I take this value for current, that's positive. So positive times a positive gives me a positive point up here for power. So for some of this, I got positive power. But if I come over, like right here, if I take this value for voltage, the value for current is negative. So I got a positive times a negative, which is a negative. So for some of these values, I want to have a negative value for power. And then over here, I got a negative times a negative, that's a positive. So for those values, I want to have positive for power. So it looks like that when I have a reactive component, at least the capacitor here, then what happens is sometimes I have positive power, sometimes I have negative power. It goes back between positive and negative power. And again, I'm not going to try to draw the power curve. You refer to the graph. And you can see what I'm talking about is true. Look at the power curve. The first half cycle of the power curve, if you look at it, the first half cycle of the shaded in gray area, the power curve, that's positive power because all the values of voltage and all the values of current, they're all positive values. So it's basically from 0 to 90 degrees of the voltage or current curve, those are all positive values you get for power. And then you have a situation where we have positive power, positive voltage, and negative current. For those, you get negative values for the power curve. And then over here, we have negative values for current and negative values for voltage. That gives us positive value. So what you'll see is the power curve starts off as positive, goes negative, and then goes back positive and continues to flow like that. So looking at the picture, and not my picture, but the graph, you can see that we have positive power and negative power. But what I said before, if I have all positive power, that represents power that's being dissipated. Power converted to heat. Anytime I have an exchange between positive power and negative power, what that is power that flows into the component and then it flows back out. So anytime that power curve is partially positive and partially negative, it's a power flow where power flows to and fro in the circuit. It flows into the device and back out of the device. None of that power is dissipated in an ideal circuit. And so I see that's true with a capacitor. Okay, well, what if I take out the capacitor and put in its place an inductor? How would that change things? If I change this to an inductor. Now, they don't do this on your sheet because, as I said before, if you understand it for the capacitor, then you also understand it for the inductor because it's the same thing. Nothing changes. Well, one thing does change. If I make a switch, then with a capacitor, I see I first and then V. If I change that to an inductor, I see E first and then I. So if I want to make that change, all I got to do is right here, flip these. This is now current, and this is now voltage for the inductor. And you can see, if I have an inductor, I see voltage first, and then 90 degrees later, I see the current. So here it represents that at t equals 0, my voltage is max, and 90 degrees later, my current is max. So 90 degrees later in time, I see my current. So the voltage is leading here. But nothing else changes. The power curve is exactly the same. I just switched the names of these graphs. I still have exactly the fact, and I'm multiplying negative current, a positive current times positive voltage, which gives me positive power for a portion of the waveform. For another portion, I'm multiplying positive current times negative voltage, which gives me negative power. And then for the other portion, I'm multiplying negative voltage and negative current, gives me back the positive power. So I have the exact same power waveform, regardless if I have an inductor or capacitor there. And so that waveform goes for both inductors and capacitors. And again, the idea here is that you can see Energy flows into the device, and then energy flows back out of the device. None of the power or energy is dissipated as heat. So the takeaway is this: if you have a resistor, the energy that flows into a resistor is converted to heat. It's dissipated. We say dissipated. If I have reactive elements, either capacitor or inductor, the energy that flows into those devices is borrowed and then flows back out, is returned to the system. Okay, well, then the next step you might think is, what if I combine elements? What if I have something like this, where I have a resistive element and a reactive element? Now, again, your diagram, the graph favors the capacitor. It could be a capacitor or an inductor or even both. It doesn't matter. You just need a reactive element. And so if I show the resistor and the capacitor, what would my power curve look like for this? Well, what happens here is, just from the picture point of view, from the picture, some of the energy is dissipated and some of the energy is stored and returned to the system. So I get the effects, I get a combined effect of what each individual component would do. I get the combined effect of both. Some of the energy is dissipated as heat by the resistor, and some of the energy is borrowed and returned to the system by the reactive element, be it XC or XL. It's borrowed and returned to the system. And so I won't attempt to draw the next graph, but you have the handout there. Please look at it. You'll see, if you look at the very first graph, where we have only resistive elements, you see positive power. You look at the next graph at the bottom, the one we just got to talking about, where we have the capacitor, you see positive and negative power representing energy that's borrowed. Well, that last graph where you have resistance and reactance, you see a combination of the first two graphs. You see the power curve, and it's not all the way above the horizontal axis, which means that it's not all resistive power, but it's not evenly spaced to where half the cycle is above the horizontal axis and half is below. So it's not completely borrowed power. It's a combination of both of those. And so you see the graph, the power curve is slightly shifted. And by adding a resistor to a reactive element, what you do, if I have only the inductor or only the capacitor, then the phase difference between V and I is 90 degrees for both of these. By adding a resistor, you should know what it does. By adding a resistor, you add that angle between 0 and 90 to it. So there'll be a phase shift. These things won't be exactly 90 degrees apart. But the same kind of logic still applies. If I make the angle less than 90, I still can do this point-by-point multiplication. And what you'll get is a graph very similar to that third diagram picture on the handout that I gave you. So the takeaway from that third picture is this: if I have a resistive element and a reactive element together, we call that impedance. If I have impedance, then with impedance, some of the energy is converted to heat, some of the energy flows into the system and returns back. It's borrowed power or borrowed energy. So that's the graph. Anybody have any questions over the graph? Anything that we talked about? This graph, I don't know where I got this from. I don't remember whose book this came from, but this is actually a really, really, really good thing to look at, because power is very abstract. I can think of current. I got a certain way I view current. I just view current as like an arrow flowing through a circuit. I can even mentally picture a voltage. A voltage to me is just, I look at it as a pressure. Pressure doesn't move, but pressure can cause other things to move, right? And I can see that. I think of resistance as an opposition, but I don't have a mental picture for power. And so I think this helps you to think about it in the right way, to see how the idea of negative power, positive power, or combination in between the two, how that kind of comes about by looking at these graphs. So I think this is handy. So make sure you keep that, worship it, store it. Now, there's another sheet, a topic sheet, which I think it got up on Blackboard. It's one title, AC power, in the upper left-hand corner. So see if you have that. If you printed it out, take that out. We're actually going to go in and define the various types of power. There's several different types of power in AC, and so I want to go and talk about each one of those. So this handout takes us through that. So if you don't have it, go ahead and get it out. And again, it says AC power in the upper left-hand corner, and that's the topic sheet for our discussion today. And at the very top of that paper, there's 3 Roman numerals. Number 1 says power in a purely resistive circuit. See handout. And the handout they want you to see is the one we just got through talking about with the graphs on it. So the first 3 Roman numerals refer to the graphs, the handout we just got talking about. So Roman numeral 1 says, look at what the power looks like in a purely resistive circuit, the power in a purely capacitive or inductive circuit, and the power in a resistive and a mixture circuit, a resistive and reactive circuit. So how do they look like? What do they look like? Well, we already showed you. Now, in that first part where those Roman numerals, they give you the symbols that we're going to use to talk about power. I want to put them on the board. There's different kinds of power. There's resistive power, there's reactive power, and there's a power where you have a combination of the two. And so what we do is we give each one a different symbol. So let's talk about that. So resistive power we'll call that PR, resistive power, or just P. The unit is watts. If I have either a capacitor or an inductor, so I got reactive power. The unit is VAR. Now, I see it with a lowercase v. I don't think I've seen it the other way, but I capitalize all of these. So what is a VAR, a VAR? VAR. Well, that's a unit for reactive power. It stands for volt, amp, reactive. Volt, amp, reactive. And the symbol we use, if I have these VARs, the symbol is the Q. So we use P for resistive power, we use Q for reactive power. So if I have only resistance, it's P, just what it was in DC, my units would be watts. If I have only reactive elements, then I don't use watts. It will be improper to use watts because there's no, watts is energy converted or work being done per unit set, per unit time. This doesn't do any work. Energy flows in and then back out. So it would be improper to call it watts. So they use another unit called a volt amp reactive, or VAR, VAR. Now, VARs, by definition, some VARs are positive and some are negative. If I have an inductor, these are positive VARs. If I have a capacitor, by definition, these are negative VARs. These are positive VARs. So that's important because if I have, a capacitor and an inductor, and I tell you the power here was 10 VARs, and the power here was 15 VARs. If I ask for the total reactive power, then what you got to do is you got to look at both those elements as one unit, because they're both reactive. So you got to look at the combination of these. You got to supply that negative sign. So I have a negative 10 bars from the capacitor. I have a positive 15 bars from the inductor. So I would have a positive 5 bars. That would be my net reactive power. So you got to remember this idea of negative and positive bars. By definition, the capacitive bars are negative and the inductive bars are positive. Well, what about if I have inclination? If I have resistance and reactance, what do I have then? If I have something like this, I have resistance and reactance. I can use that, I can use an inductor, I can put both there. If I have a combination of, I have some R and some X net, then it wouldn't be watts, because some of them participated, but not all of it. It wouldn't be bars, because some of the power is borrowed, but not all of it. It's a mixture of the two. So what they do, if I have a combination, they call that, they use a symbol S, and S is called apparent power. Apparent power. And the symbol we use for S is the VA. The symbol we use for S is VA. That stands for volt amps. That's another form of power. When you have a mixture of resistive power and reactive power. So that's a lot to wrap our minds around, but let me go back to the sheet. Just want to read from the topic sheet because I think it's pretty clear. At the very top of the topic sheet, below the first 3 Roman numerals, it talks about true power or resistive power. And it shows you, we use the letter P as in Paul to represent power, as I said here. The unit will be watts, and then it says the average power consumed by the circuit during one complete cycle of alternating current. True power is the rate at which resistance in the circuit converts the electrical energy to heat. So we defined that already. But notice the formula's there. That's what you learned about in DC. That power is I squared R, power is V times I cosine theta. Or you can even use the other one where power is V squared over R. The same formulas that we used in DC apply in AC. You can see it, if you go back with our power equation, our fundamental power equation, Watt's law, in DC was power equals voltage times current. In DC and AC, we write it the same way, but power equals voltage times current times this power factor. The power factor is the cosine of the angle between these two. Remember, if I have a resistor, the current and voltage are in phase, so that this angle between them would be 0 degrees. And you know from your trig class that the cosine of 0 is 1, so this goes out as 1, and I got my original circuit back, my original equation back. So this works out. In AC, the power equations are exactly the same as in DC as far as the resistor is concerned. And even the reactive elements use the same formula, but if I'm talking about reactive power, where I would have P is I squared times R, well, Q, the reactive power, is I squared times X. So I use the same formulas. I just substitute the R for the X, and I can use all the various forms of Watt's law in AC as long as I do that. But anyway, back to the sheet. So the first thing they talk about there is true power or resistive power, and they give you various ways to calculate it. And then they go down and talk about reactive power. Now, reactive power is also called imaginary power. I'll tell you why here in a little bit. But they show you the symbol Q, and the unit is the volt amp reactive, VA reactive. And notice in the parentheses it says inductive or capacitive. What that means there is, let's say you go back to this. There's two ways to show the solution there for the total power. I can say I got a negative 10 bars, and I got a positive 15 bars. So my answer is a positive 5 bars. So that's one way to show it. Another way to show it is 5 VAR inductive. Because my inductive power was bigger than the capacitive power. So the fact that the power left over was positive means that these bars are inductive. So I can show, if I show the positive sign, I don't have to write the IND after it. If I don't show this, then I want to show the IND to identify what kind of bars we're talking about. So that's important. Back to the sheet. So let me read what it says for reactive power or imaginary power. It's also called wattless power. Wattless power. It is the power value obtained by multiplying the effective or the RMS value of the current times the RMS value of the voltage, sine of the angular phase difference between the voltage and the current. Reactive power is not dissipated as heat. It is returned to the generating system. So we've already talked about that, the fact that reactive power is borrowed power. And then the last one is apparent power. They use a symbol S. The unit is a VA, volt amp. And it says there the power value obtained in an AC circuit by multiplying together effective voltage and current, which reach their peaks at different times, because there's a phase difference now. Because resistance is being mixed with the reactance. That causes them to peak at different times and give you the phase difference. And then at the very bottom it says S is determined by the power triangle. S, the apparent power, is determined by the power triangle. So let me relate it to DC. In DC, the total power is equal to the voltage times the current. In AC, the total power is called the apparent power, S. In AC, the apparent power is, well, to get that, you got to use the power triangle. You just don't multiply these two. Now, there is an equation I'll talk about, VI times I star. So you go ahead and write this down, and I'll explain that. It says that the apparent power is the voltage times the current. That star means conjugate. We'll talk about I star later on. So write it down. We'll come back to that equation. So I want to talk about the power triangle. What is the power triangle? Let's look at it. Let's look at an impedance diagram. Consider this. If I got an impedance diagram, where I got R and X, and let me take any old point in the complex plane. I just pick any arbitrary point like this one right here. Well, if I pick that point, then what I get is two things. What I get right here is a certain amount of resistance. What I get right here is a certain amount of reactance. And if I do the diagonal to origin, then what that is impedance. Z equals R, go over R units, and go up or down, plus or minus JX. So we've seen that from other calculations, no surprise there. But notice what I get here is I get a right triangle. That's a right angle. So what I really have is a right triangle that I can get from the impedance diagram like this triangle right here. That right triangle. If I bring it over here, I have this right triangle where this is R, this is X, and this is Z. And that's a right angle. And this right here is theta Z. That's my impedance angle. Theta Z is my impedance angle. Now, you guys know from math that if you have an equation, you can multiply an equation. Really, you can do anything you want to an equation as long as you do the same thing to both sides. You know from your math class that if I want to multiply both sides, if I want to multiply one side of the equation, I can do it so long as I multiply the other side the same value. Equality is maintained. I can do whatever. If I want to paint one side of the equation white, I don't change the equation as long as I paint the other side white. Whatever I do to one side, I got to do to the other side. Well, with triangles, we have three sides. With an equation, it's the left or right side. With a triangle, I got three sides to define a triangle. With a triangle, I can do whatever I want to a triangle so long as I do the same thing to all three sides. I maintain the triangle. I get a bigger triangle or a smaller triangle, but they're all similar triangles and they basically have the same relationships. So what I'm going to do is I'm going to choose to multiply this triangle by I squared. I multiply that by I squared. Now if I do that, if I just multiply this one side by I squared, it'll extend or decrease the side. What I'm going to do is multiply all three sides by number I squared. Whatever that number is, I'm going to multiply each side by it. And you can see what's going to happen. I'm going to get a bigger or smaller triangle, but these angles are going to stay the same. So we call that a similar triangle. And in geometry, when you have a similar triangle, they're equal. You know, if you take the sine or cosine or tangent of similar triangles, they're equal. So that doesn't really change the value of the triangle. But notice what I've done here. If I take I squared R, you might recognize that as power. P equals I squared R. If I take I squared times a reactive element, then it won't be P, it'll be Q. Q equals I squared times X. If I take I squared times the total opposition, which is called impedance, then we call that S. S equals I squared times Z. And so basically I changed this triangle to this one. This right here gives me P. This right here gives me Q. And this right here gives me S. So where this came from the impedance diagram, we call this the impedance triangle. If I take the impedance triangle and multiply all the sides by the square of the current, then I get the power triangle. The power triangle. And that's what they mean on this paper. It says that apparent power is determined by the power triangle. So if I want to know the apparent power, I got to use the power triangle. So what do I mean by that? Well, you know that anytime I have a right triangle, now I can use Pythagorean theorem. So if I write out the formulas for this, S squared would equal P squared plus Q squared. If I take the square root of both sides, I get the formula for apparent power. And remember, the unit for this is the VA. VA. Here's something interesting. This angle right here And remember, this triangle came from here, so this angle and that impedance angle are the same. So my theta z is the same as the theta over here. I'll call it theta p for power. But it's the same angle that, remember we had this cosine theta? And we'll come back to that, but that cosine theta, we call that the power factor. Well, that angle right there and this angle right here are the same. So we'll end up using the fact that that power angle and the angle here, that's the angle between the volts and the current. They're the same angle. That could be useful information for later on. So the takeaway is that I use the power triangle when I want to calculate S, or I showed you the other equation that I said we'll talk about later on, where S is equal to VI times I star, where the star is called the complex conjugate. We'll do that later on. Now I want to focus on the power triangle. So that's a lot. We went through the graphs, we went through the topic sheet, and now we have an example at the bottom of the topic sheet that I want you to do. Before we get into the example, anybody have any questions or comments about anything we talked about so far today? The graphs or the handout? Anybody have any questions? We got resistive power, we got reactive power, we got apparent power, the symbols and the units. Anybody have any questions on any of the information so far? Okay, well, I want to proceed to the example then. This will help drive some of these concepts home, hopefully. So if you don't have it, get a sheet of paper. You'll need a calculator, a piece of paper, and what I want you to do is to read the example problem, draw a circuit for the example problem, write down what you know, and write down what you're looking for, and see if you can solve the example problem. So go ahead and read. I'll read the problem in case you don't have it, but you should have it out. It says calculate the following for an RC circuit if R is 2.2K, XC is 3.3K, and the voltage is 5 volts with a phase of 0 degrees. They want you to find the total impedance. They want you to find the current. They want you to find, I can't read that. I can't read it. They want you to find P, Q, and S and the power factor. So find all those values. Oh, and by the way, since we're talking about, I put a new homework up, so I don't know if you guys had a chance. I think I put it up Sunday. So go and look at that because it's due. It's not a whole lot, but it's a fair amount of calculations. All series circuits, just to drive some of those points home. We did the circuit analysis, the circuit configuration stuff. So have a look at that, and hopefully it's straightforward, but if not, you can ask me questions about it. Go ahead and get a piece of scrap paper out, and I want you to draw the circuit and try to solve it. And I'm going to be quiet for a minute, turn my mic off, and let you guys try to work on it. And then we'll come back and we'll work it together to see if you got it. So try to solve the example problem. Then we'll give you guys a little bit of time to do this. I'll move out of the camera frame, but I'm still here. Here's the circuit. Let's find a Z. This is the impedance angle or the total angle. They're all the same. Power, parent, reactive apparent, and the power factor. See if you can find all of that, and then we will review it. I'll give you a few minutes to work on it, and we'll review it together shortly. I'm going to turn my mic off, but I'm right here. All right, you guys are calculating. Keep on calculating. I'm gonna go in and we'll start working on this. So it wants to find the total impedance. That's stuff we've done before, so it's nothing earth-shaking there. Let's go ahead and solve it. So I'm looking this way in the circuit. My impedance Z will just be the resistance plus the reactance. So what I get is 2.2 minus J 3.3, and this is in K ohms. So I need for you to convert this to polar form for me. So somebody convert it over. Let me know what you get when you convert this over to polar. Z is what in polar? Let me know when you got a number. I misplaced my calculator somewhere, so I can't do any calculations at all.
Are we waiting for a polar form?
Yep. You got it?
I got 3.96 at a phase angle of 56 degrees.
That should be a negative 56, right? You divide a negative?
Yes.
Okay. And then this would be
Kilo.
ohms. All right. So if we go with that for our impedance, let's see what else we can find. I'm surprised they didn't ask us for current. They didn't ask us for current on the sheet. Let me see where to do my
They
sheet.
did.
Oh, I left it off up here. So let me add that to the list. Because that would be the next thing I want to find is the current. And once we get that, then we can get that right there. So let's do the current next. I guess this is a good review of the stuff that we've done. So my current now is a phasor. So it's going to be my voltage phasor over impedance, 5 angle 0. This is 3.96 angle minus 56 degrees. Now this is K ohm. That means my current is going to be in milliamps. So what's 5 divided by 3.96? How much is that? 1 point what? 5 divided by 3.96.
1.26.
Oh, my hand and my brain are not in phase right now there. 1.26, the angle is 56 degrees. milliamp. Now you can see my voltage is at 0 degrees and my current is at 56 degrees. So this stator right here is 56 degrees. If you draw an impedance diagram, you can really see it. I always like to draw it because I kind of can get an idea where things are. So always work off, the phasor diagram, not the impedance diagram. But my voltage is my reference at 0 degrees. So my 5 volts is right here. That's my total voltage. And my, where is it? My current is at 56 degrees. So my current is like 56 is probably like right there. Right? That's my total current. And remember Eli the Iceman? Eli? Iceman? I got a capacitor here. So my phasor diagram, I would expect to see the current and then voltage behind the current. And that's exactly what I see. I got these two phasors rotating, my current phasor, my voltage phasor. If I look through that smaller angle, I see if my eyeball was right here looking at these rotate, then I will see the current phasor go by, and then 56 degrees later, I'll see the voltage phasor go by. So I can tell that. And since I know this now, then I can get, so we got this. I can also get the power factor because it's just going to be PF is cosine 56 degrees. What's the cosine of the 56? Make sure you're in degrees and not radians. What's the cosine of 56?
0.56.
0.56. Now, when you give the power factor, I think I said this before, I don't remember. When you give the power factor, you always got to say leading or lagging. If you just give me 0.56, I'm going to mark it wrong. It's either a leading power factor or a lagging, and the current, it follows the current. So I erased the phasor diagram, but you know the current was leading, and the voltage was 56 degrees behind it. So I would say 0.56 leading. That's the way you report the power factor. So we got that one. We got that one. All we got now is power, just power. So that's pretty easy. So when you do power, what you want to do is work off the power triangle. So let's put the power triangle up there. So on the power triangle, what I have, I got P, I got Q, I got S. So what you do is you use any form of Watt's law, like, P equals I squared R, P equals V squared over R, P equals V times I. I can use any of these forms to get the two legs of the triangle. Of course, if I'm using this instead of R, I have X's there. But use any form of Watt's law to get the two legs, and then we got to use Pythagorean theorem to get the hypotenuse, which is the apparent power. So go ahead and do that if you didn't already do it. And I guess the most convenient thing to do, since we got the current, well, I erased it. I forgot what it was. What was the current again? Somebody give me the current value. What was it? It was 1.3?
1.26.
I think that the angle was 56 degrees. So since I got current, I guess I squared R would work just as good. Let me get a darker marker. So I'm going to find P. P equals 1.26 times 10 to the minus third. I guess I should put my units in there. I got to square that and then multiply by 2200. Let's do it that way. So do this 1.26 times 10 to the minus third squared times 2200. Give me the value for P.
I got 2.77.
Okay, so this will be watts. Okay, 2.77 watts. And then what you want to do is, let's get Q, same way. So Q is going to be 1.26 times 10 minus third squared. Again, I put my units in there, times 3,300. Let me know what you got for that one.
4.16.
I got different
Right.
answers for both of those. I'm not sure if I'm doing something wrong.
Okay, what'd you
For
get?
for the first one, I got 3.5, and for the second one, I got 5.2.
All right, now is there a third person doing the calculating out there, or just you two? Anybody agree with either one of these? Who else out there? I got Dominic and I got Randall participating, but I also have Tresser and Jacob. Man, where's the class? And one person called in. I guess the nice thing about calling in is I can't see who you are, so I can't call on you. But either Jacob or Tresser, did you? Anybody agree with one of these? Is it the 3.5 and 5.2, or is it the 2.77 and the 4.16? Which one is it? And then, you guys can just turn the computer on and walk away from the thing. I don't know if you're really there or not, because all I see is these little icons. And I haven't heard Jacob say anything, so he might not even be. It could be. He could just have his computer logged in. Tresser and Jacob.
Don't call me out like that. Hold on 1 second. Hold on.
I need somebody to break this tie. Well, it's not a tie, but we got 3.5, 5.2, or do we go with 2.7 and 4.16? And make sure you use the parentheses on this. If you don't, you might get the wrong answer. So you guys might want to recalculate, put parentheses around here, and when you do this part right here. Now, I hope he doesn't come up with a third set of answers. That would be terrible.
Yes, that would be a disaster.
You said a degree, right?
Say it again.
You said it's a degree, right? That's what you wanted? You said degree, not radian, right? Yeah,
So
that's what you wanted in, right?
For this, it doesn't matter.
Our calculator's supposed to be in degree right here. Okay.
Only when we're doing an angle, but for this, it doesn't matter. So I just want you to do It can be, it doesn't matter when you're doing just a regular calculation. It only, leave it in degrees. Just leave it in degrees, but to do this, it won't matter if it's in degrees or radians. I just want to know what 1.26 times 10 to the minus third squared times 3,300, what is that? Is it 4.16? Or is it something else? So recalculate it and see. I can't believe we're stuck on this.
Does that say 1.26 times 10 to the negative third squared?
Yep.
I can't see the. Oh, okay, I got it wrong then. Mine's wrong then. I'm sorry.
What did you get?
I didn't see that square at all.
What, so one of these numbers. So 1.26 times 10 to the minus 3 squared times 3,300. Dominique's claiming that it's 3.5. Is that right?
No, that one should be 5.2. The times 3,300 is the 5.2.
Okay, so that's this one. So we're saying that this is 5.2, and this would be in.
Should be milli, right?
This is
Yeah, milliwatts.
yeah.
Yeah, he's right.
Yeah,
My bad.
we
I
do.
didn't see that too. I didn't see the square. Yeah, he's right.
Okay. So this is milli VAR. So that would be milli VAR, and then this would be 3.5 milliwatts. Is that what we're going with?
Yeah, I'm with him on that.
Okay. And so now to find, remember, you can't just multiply this times this like you do in DC. Is what you got to do to find S. S is the square root of P squared plus Q squared. So that's how we find the apparent power. And we've already found this angle right here. It's the same as the impedance angle. It's just 56 degrees. So we know we get that as a gift. So we know that theta there is 56. Same as the impedance angle. So let's do this now. We'll do 3.5 squared plus 5.2 squared square rooted. And since these are in milli, our answer is going to be in milli VA. So let me know when you got a number for that. I guess I can keep my purple marker. All right, so what do you get for this? And I suggest you put parentheses around it to force your calculator to give you the right answer. Let me know when you got an answer.
I got 6.27, but don't quote me on that.
I got 6.27 as well.
Agreed.
All right, so we're done. So there you go. There's the power triangle showing now, did we do the power factor or not? I got it checked off, but I don't see the number. Did we do the power factor?
5.6 leading.
Okay, now look at this
It's still written
0.56.
right on the board, isn't it?
Where? Oh, no, right here. It was in a snapshot, bigger than day, right? Now notice 0.56. Look at that. Let me just point something out to you real quick. Remember what we said about power factor? If I have a power factor, if it's 1, then my circuit is 100% resistive. If it's 0, it's 100% reactive. What we usually want is this. So I'm like, that's about 0.6. So on the scale, I'm not quite halfway. I guess I'm a little more than halfway. So power factor is about right there. So it's closer to resistive than reactive. Why do I want it to be resistive? You got to remember that resistive power is the only power that can do work. So what kind of work? Well, let's say I have an electric motor or a light bulb, or it really doesn't matter. Any electrical device that has reactive and resistive components in it. The power flows into the device. Only the power that's dissipated as heat can make something move, can do work. So any other kind of power is just wasted, it's useless. It goes in, takes up room, and it flows out. So we don't want that happening. So what we like to do is to get this up as high as possible. And you might think to yourself, well, that's easy. Just add more resistors to the circuit, but it don't work like that. Because think about a motor. A motor has a coil inside of it, and that coil, it's not a real resistor in there, but the coil itself, the resistance of the wire, is what takes place as the resistor. You can't add a resistor to that. You change the characteristics of the motor. So the answer is not adding more resistors. We gotta, if I want to get that power factor up, we gotta do something else to the circuit. And that is like the third lecture on power. We got this lecture, we got another lecture, we got a third lecture that actually tells you how to get that power factor up to a better value. You'll never get it all the way up to 1. I shouldn't say it'll be difficult to get it up to 1, but you can get it up higher and make the circuit more efficient. The closer it is to 1, the more efficient the circuit. Okay, so that's a good example problem, guys. Now, we got the AC Power Practice 1 sheet. I think I put that up on Blackboard. So let's go to that. And what I want to do, we have a bunch of practice problems on here to help reinforce these calculations and just get used to doing them. None of them are particularly hard, but let's go ahead and let's solve these. So if you have the sheet gives you, at the very top, it says, for each figure below, determine the real and reactive power. The real power, or the true power, is resistive power, and the reactive power is what it is, reactive power. They give you 3 circuits. For each circuit, tell me Q and tell me P. That's what they want, Q and P for each circuit. So you go ahead and do those, and I'll put it on the board. We'll put them together in just a second. You go ahead and do it first, though. Work it out first. All right, so there are our three problems. We want to know P and Q for each circuit. Give you about another minute or two. This one's pretty simple. For this first circuit, we don't have any reactive components. So for this one, Q is 0. And for this, we don't have any resistor. So for this one, P is 0. And the same here, we don't have any resistor value here. So for this one, P is 0. But over here, I do have resistors. So I can get P over here. P, if we use V squared over R, we can actually use that form of Watt's law to solve for all of these. So I got my voltage magnitude is 100. So I got 100 volts squared divided by 5. Over here, I got 100 volts squared divided by 20. And over here, I got 100 volts squared divided by 40. So what you do when you take 100 squared, I guess that's what, 10,000 over 25 is what? A 100 squared divided by 25.
400.
So 400 watts. Over here, now we got, is that 800? No, it wouldn't be 800. I don't know how I'm thinking about this. We got 100 squared on 20 is what? Is that 10,000 on 20? Is it 500?
Yeah.
Watt. Oh, that's wrong, isn't it? It's not 500 watts. It's 500 what?
R.
It's not watt. Yes, VAR. VAR. And to be correct, since that's, I should say, well, I don't have to show it if I show it positive, but I can show positive or I can say inductive. That can be important because if you have more than one reactive component, you gotta know whether to add or subtract. So you want to show either a positive sign or state that it's inductive explicitly. And then this one, 100 squared over 40 is what? I'm too tired to do the head math right now.
250, 250.
This is VAR capacitive. That was pretty easy. It wasn't nothing hard about that once you see what we were doing. So that wasn't too bad. Look at the next problem though. On the next problem, they give you a series circuit. They want you to find P and Q. We might as well find S too. I mean, you know, what the heck. For that second circuit, give me P, give me Q, and give me S, given XL, given R, and given the current. Give me all three power quantities.
Sorry, say, which one are we doing? The second one?
Uh-huh. Yep, going right down the paper. All right, so I want all three, P, Q, and S. And I guess, you know, for this one, we're going to use P as I squared times R. So for P is going to be 5 amp squared times 4 ohms. QL is going to be 5 amp squared. That's not right. That's a 3. This is a 4. All right, so we do that one. 25 times 3. We got 75 watts. 25 times 4. We got 100 VAR inductive. Or I can show it as a 100. And then to find S, you gotta use Pythagoras. S is gonna equal 75 squared plus 100 squared, square root it, and make sure you put that in parentheses. So your calculator will give you the right answer. Anybody got a value for S?
I got a 125. Sorry, my connection's kind of choppy. I got 125.
125, that's about right. And this would be VA. All right, so if you wanted to, you can show your power triangle there and ask for it. We got 75, we got 100, we got 125. And this right here, that angle right there, is related to the power factor. So there you go. Again, that wasn't bad at all, was it? Once you see what you're doing. All right, well, let's jump down to the next one. Look at the third problem, or the 1, 2, 3, 4, the fifth problem. This time they give you a parallel circuit. They want P and Q, but again, let's go ahead and get P, Q, and S. Let's just do all of them. So they give us a voltage of 4 volts. We just assume it's AC voltage. They give us a resistor and a capacitor in parallel, 80 ohms for the capacitor, 20 ohms for the resistor, and wants to find P, Q, and S. So clearly we're going to use the other form of Watt's law. P equals V squared over the opposition. So for the resistor, we get 40 squared over 20. And for X or QC, we get the same 40 volts squared because they're in parallel, they got the same voltage over 80. So let me know what you get for power. Anybody got 40 squared over 20?
Came up with 80.
80 watts. What about 40 squared over 80?
$20.
Isn't that weird? Capacitive. So if I take 40 over 20, 40 squared over 20, I get 80. If I take the 80 and put it here, 40 over 80, I get the 20. Fascinating.
Now, when showing us capacitance, we can just put the negative sign in front of the 20.
Yep, you can just say minus 20 VAR. At that point, you don't have to show this. You can show both. It's like wearing a belt and suspenders at the same time. It's kind of silly, but you can do it. But either this or that. I use them both, interchangeably, just depending on how I feel at the time. So that was easy. Oh, we got to get S. I said I wanted S too. Let's get S real quick. So S, now when I do S, I don't have to take into account that that's negative. I can just use the, I can just use the 20. I'm not really concerned about negative or positiveness there. What do we get for S?
Got 82.5 VA.
All right, we'll go with that. Nobody disagrees. We'll call those the correct answer. And again, if you understand DC power, this isn't too bad. Not yet, anyway. Well, it's 3:54, and we got one more practice problem to do, and that's going, let me see. I think this is it. Because practice number 2 deals with parallel, but that's a simple modeling problem. So we don't have to worry about that right now. But this last one I want to get. So look at that. You got a series parallel circuit on the bottom of the page. They want you to find the total P, the total Q, and the total S for the circuit. So that'll take you a couple minutes to do. So I'm going to be quiet, and you go ahead and you work that out. I'm going to put the circuit on the board so we can talk about it. So let's work it out, and then that'll be it for today. We'll call it a day. I think that was a good workout for us. Introduction to AC power. All right, so we got the circuit. We know in this part of the circuit, the main lines, we have 20 amps flowing through R and XC1. And over here, they tell us the voltage across XL is 200 volts. So I'll be quiet, give you a couple more minutes to work on it, and then we'll talk about it. All right, guys, keep working. So I made this little table here, and what we got to do is figure out the power for each element by itself. Some we have series currents. We got the series current for R and XC1, and they tell us the voltage across XL, but since XL is in parallel with XC2, we know the voltage across both of those. So we just find each individual power. So let's start by doing the resistive power. We can get PR for the resistor. There's only one resistor, so I'll just call it P. And that's just I squared R. So it's 20 amps squared times 3. 3 ohms. And 20 times 20 is what? 400. So is it 1200 watts? I think it's 1200 watts. So over here, I'm going to put 1200 watts. And that's the only power I have. I can get, we'll call this QC1 the same way as I got this power. It's going to be 20 squared times 6. So what is that? 400 times 6, 6 times 4. Is that 2400? Make sure I'm doing my arithmetic right because I'm really tired, I'm hungry, and I start to mess up. So I think it's 26, I think it's 2400. But that would be a negative. This is what Dominique was pointing out. Right here, that would be a negative 2400 VAR because it's capacitive. Now you can see what I'm doing on the table. I can just tally everything up. Well, the power from here, we'll call it QC2. Now I'll switch from using this form of Ohm's law to V squared over X. So I got 200 volts squared over 10. I'm leaving the units off now because I'm getting lazy. And you tell me what this is. I don't want to think about that right now. 200 squared divided by 10 is what? Should be divided by 10. 2,000? I think it's 2,000, so I get a negative 2,000. I did.
It's 4,000, isn't it?
Yeah. Is it 4,000?
Not. I think it is, right?
Yeah. I think you're right because I got 2 squared. You gotta forgive me. I went to Cincinnati public schools.
Oh, wow.
All right. And then the last one, 200 squared on 5. How much is that?
I
200
got 8,000.
squared divided by
I got 8,000.
8,000. Okay. Now, since that is from an inductor, that's a positive 8,000. Now you can see why I put it in a table form because we can just tally it up now. My total reactive power, my total resistive power. So my total resistive power is 1,200 watts. My total reactive power, if I subtract these, I get 4,000. Subtract 2 more thousand from it, I get 2,000. And then subtract 400 from it. Is it 1,600? Did I do it right? Is that right or not? 8,000 minus 4,000 minus 2,400. Is it 1,600?
Yes.
Okay. All right. So now we gotta find S, and that's it. We're good to go. And of course, that's just Pythagorean theorem. All right, so S equals, what do we got? 1,200 squared over 1,600. And you guys should be putting the units in there, but that's like me telling you not to smoke and I'm blowing cigarette smoke in your face. I should practice what I preach. But if you do this, what do you get for S?
$2,000 VA.
2,000 volt amps. Okay. So that's it, guys. That's our introduction to AC power. And now it's all uphill from here. We got, AC, the next sheet isn't too bad. But then we get to the thing on the power factor. It's not bad. It's just a lot of trig and logic. So if you can understand trig and you're a logical person, it shouldn't be too bad at all. Now, before we sign off, I do have another lab. I'm trying to do stuff where we don't need to use the oscilloscope right now. We're trying to get us up on campus for at least one day to put our hands on the oscilloscope. So this next lab is the next two labs are going to deal with capacitors. I think what I'm going to do is just put all the labs up, and instead of doing one a week, since the time is getting away from us, I'm just going to put these labs up. You can kind of do them as you get to them. But this next one is on capacitors. The first part of it is just kind of a research type thing. So I'm going to go ahead and put that up, and you can do that. And then the next one, you actually have to use your meter, and you may need your the trainer. We'll see. I got to look at it. But I'll put this up, if not today, then by tomorrow. So keep an eye out for that. You have a homework assignment up there. It's a lot of series stuff, calculations for some practice. I'll put some parallel and some series parallel up there for you to practice with. And then we'll come up to the power stuff. I'll give you some of that stuff in a few days. So just kind of don't wait till the last minute. Try to stick with those due dates, since most of the stuff is time. One last thing before you guys sign off. I need you to send me an attendance text. You're going to text me at 494-6162. And what you want to send is your name, first and last name. Make sure in the text you put the class as ET.
No question.
132.
I'm not sure how many times I've sent that message. Were those all counted as like absences?
No. Well, as long as you send it at least once during the first 2 weeks.
Okay.
Here's what happens.
Okay.
If you're enrolling the class and you don't, normally we're face to face, so we wouldn't do this text thing. Let's say you you signed up for a class, but either you didn't show up for the first 2 weeks, or you showed up for the first 2 weeks and you didn't sign in. Well, the school is going to look at you as not being enrolled. And what they're going to do is they're going to cancel you from the class, but you still got to pay for it. That's why I mentioned it's important, and not just my class, any class, that you sign in for the first 2 weeks. Now, the reason we do it after that is, let's say either if you withdraw from the class, or if you get an F in the class, either fail it or you withdraw it, the college is going to want to know when was the last day you were in the class.
Right. Okay.
So normally I have to sign in. I can go back to my attendance records and see when the last time you signed in. But since you're doing the face-to-face thing, the remote thing, I got to have a way of going back. So if you didn't do it, as long as you did it during the first 2 weeks, you're good. And I know that you did because you're still on you're still in my grade book. If they had canceled you from the class, you wouldn't appear in my grade book anymore. So you're there. But you do want to do it because not that you're going to get an F, but if you do get an F, I got to be able to say when the last, if you get an F or you withdraw, I got to be able to say the last day you were in class.
Right. Okay.
That's all. Okay, so go ahead and you guys text me here. And Dominic, can you, I'm going to put a number. I want you to call me if you can at this number. I don't know if you can see it.
Yeah, I have it.
Oh, you do? Okay, call me at that number. And you guys, anybody else have any other questions?
I do. One more question. I'm sorry, I don't know if someone was speaking already, but I was wondering, like, are there going to be any solution sheet? Well, not a solution sheet, but I had missed a few problems on homework too, and I don't know exactly which ones I missed.
I think if you look at homework, I put a comment. I should have told you which one you missed. Usually I say, hey, you missed problem number 4. But what I said was I wanted you guys to look at the homework and the quizzes. And if you missed something, try to figure out what you did wrong. If you can't figure it out, what I said was, like during one of these sessions, you can ask me after class and, you can bring out your paper. If you can't figure it out, we'll work it out on the board.
Okay.
What I'll do is stop the camera. And so what you got to do is go back, look at Blackboard. It should be a comment on which one you missed. Okay. And then just download homework 2 and then try to figure it out. If you can't figure it out, or if you don't know if you got it right, then you can ask me after class, or you can even text me and I can meet you online or something. We can work it out. But I do want you to look at it and make sure you understand what you did wrong.
All right.
If you do that.
Okay.
Okay. Anybody else have any questions? Okay, well then you guys have a great rest of the day. Look for me to put that lab up either today or tomorrow, and I will see you guys on Wednesday. And Dominic, if you can call me at this number, I'll be waiting for your call, and I will see you guys later. Have a great rest of the day, guys. Thank you.